Welcome to the Foundry by Forge College. Let's jump right in, shall we? Today, we're pulling out the engineering blueprints to explain the mathematical wizardry that actually secures the blockchain. We're talking about cryptographic hashes. If you've ever found yourself wondering how blockchains guarantee that absolutely nobody tampered with the data without forcing everyone to store a bajillion gigabytes of backups, well, this is the secret sauce. Let's get into it. Okay, here's our blueprint for today's explainer. First, an introduction to cryptographic hashes. 2, determinism and fixed size. 3, the 3 resistance properties. 4, triggering the avalanche effect. 5, fingerprints, locks, and lotteries. And finally, 6, securing the blockchain foundation. We're building this right on top of the concepts you scoped out in our previous capstone proposal lesson.
Section 1. Introduction to Cryptographic Hashes, the engine of data integrity.
Before we build a blockchain, we need the engine that makes tamper-evident logs actually work. Think of a cryptographic hash function like a giant mathematical blender. You can throw absolutely anything into it, a single word, an image of a cat, or literally the entire text of the internet. Hit blend, and it will always spit out a uniform, neatly packaged output. We usually call this output a hash, a digest, or a fingerprint. Without this, a blockchain is really just an incredibly slow, highly hackable database.
Moving on to Section 2, Determinism and Fixed Size, the core specs of the machine.
Now check out the stark contrast here. Whether you toss a massive, multi-volume encyclopedia or just the single letter A into the machine, it is always going to produce a predictable 256-bit summary on the other side. This fixed length is a real game changer because it makes storage incredibly cheap. Storing a tiny 256-bit hash per block header is blazingly fast compared to dragging around whole previous blocks just to check if someone messed with them.
And that brings us to determinism. See the factory press perfectly stamping out those identical tokens? That's exactly it. If you feed the exact same input data into the function, you must absolutely always, unconditionally, get the exact same digest out. This is totally vital for independent verification. Honestly, if the function were unpredictable, the entire trustless nature of the blockchain would just collapse overnight.
Section 3, the 3 resistance properties. Stress testing the hash.
Having a predictable, fixed-size machine is nice, but blockchains live in a pretty hostile world. Let's stress test this machine against attackers. Each specific resistance you see here maps directly to defeating a different kind of threat. First up, pre-image resistance means it is mathematically impossible to reverse engineer the original data just from the hash. There is simply no unbaking the cake. Second pre-image resistance means you can't maliciously craft a fake document that accidentally produces the exact same hash just to frame someone. And finally, collision resistance means it's incredibly hard to find any 2 random inputs that produce the same digest.
But you might be wondering, okay, if the output is always exactly 256 bits, what is stopping a sneaky attacker from changing just one tiny comma to forge a document while keeping the hash looking mostly identical? It's a brilliant question, and the answer is delightfully chaotic.
Which leads us to Section 4, triggering the avalanche effect, chaos by design.
This is literally one of my absolute favorite mechanics in all of cryptography. Change just one tiny pebble, literally one single comma in a massive 1,000-page essay, and the whole hash explodes into an unrecognizable chaotic avalanche of ones and zeros. A tiny input change alters roughly half of the output bits, completely obliterating any predictable pattern. An attacker can't just tweak a document and guess what the new hash will look like. They have to start all over again from scratch.
Section 5. Fingerprints, locks, and lotteries, the user manuals.
Now, I know pre-image resistance sounds a bit like textbook jargon, right? So to make these specs super intuitive for your real-world designs, let's look at 3 highly practical mental models. These 3 models, the fingerprint, the one-way lock, and the lottery ticket, act as your quick reference manual. They'll help you instantly evaluate which mathematical trait you actually need for the operation you're trying to secure. Let's break them down real quick.
First up is the fingerprint model, which perfectly illustrates pre-image resistance. Think about it. You can't magically clone a person's entire physical identity just from a smudge left on a coffee mug, right? But if you have 2 matching prints, you know it's the exact same source. Hashes work the exact same way. Matching fingerprints guarantee identical data without ever revealing the data itself. Next, we have the one-way lock model, representing second pre-image resistance. Imagine locking your data into a heavy steel box that snaps shut. The hash digest is essentially the token proving you locked that specific data inside.
It totally prevents anyone from pulling an Indiana Jones-style swap, swapping the actual contents for a bag of sand while somehow keeping the exact same token.
And finally, the lottery ticket model for collision resistance. Mathematically speaking, since inputs are infinite but the output is completely fixed, collisions must exist somewhere out there. But finding two different inputs that create the exact same hash? It is like finding one specific winning ticket in a pile the size of the known universe. The sheer brute force cost makes it practically impossible.
Section 6. Securing the blockchain foundation, putting it all together.
Now that we deeply understand the blueprints, it's time to zoom out. When you're designing Web3 architecture, you should always follow three core principles. First, match the specific resistance property to your threat model. Remember, a hash isn't just some magic wand. Second, tune your output size based on how much brute force an attacker might realistically have. And third, use those mental models we just talked about to clearly communicate your intent to your fellow engineers.
I absolutely love this quote. A hash function compresses information, but compressing is not the same as hiding. The security guarantees come from the difficulty of reversing that compression. It brilliantly summarizes our foundation today. We aren't just shrinking data. We're putting it through an irreversible, one-way mathematical meat grinder. And that perfectly sets us up for our next module where we will actually calculate the exact mathematical costs of various attacks.
So I'll leave you with this final thought to ponder. If a 256-bit lock is currently unbreakable, what happens when future attackers build much bigger mathematical hammers? As computational power grows, especially with quantum computing looming on the horizon, how long will our current cryptographic locks actually hold up? I highly encourage you to visit forge.college to learn more about quantum-resistant algorithms and to explore our other foundational Web3 topics. Thanks so much for joining me on this explainer, and keep building secure systems.